So that gives you 1 is equal to a times s plus 1 times s plus 2 plus b times s plus 2 times s plus c times s plus 2. You plug in s equals to 0, you get 1 is equal to 2a. You plug in s is equal to minus 1, you get 1 is equal to minus b. You plug in s is equal to, wait a minute, did I do that right? I think there's an error here. That was supposed to be s plus, this is supposed to be s plus 1 here, yeah. So the point is, you have distinct roots, so the partial fractions is really easy. You can just plug in the roots and you get 3 stupidly simple equations. That's 0, that's minus 2 times minus 1, 2c, right? So therefore, f of s is 1 over 2s minus 1 over s plus 1 plus 1 half 1 over s plus 2. Are you getting this, Belu? And so the inverse Laplace transform of that is easy enough. It's just 1 half minus e to the minus t plus 1 half e to the minus 2t. Right? And knowing that, I can then go write down the solution. I can go back up to what I'm about to write. I'll write it in green. So I can take this, go back up here, and write down my answer, which is parentheses 1 half minus e to the minus, and then you gotta be careful, that t becomes t minus 2, gotta evaluate, plus 1 half. We really should assign these to pre-calculus students because it's really great practice with function composition, you know? Like, look at all this function composition, it's so exciting. One of the main things differential equation students get wrong, though, is this function composition, because they never really understood it symbolically when they were supposed to, and now they're paying the price for it in this 300 level course. Oh well, this is why we can't have nice things, but there it is. That starts at 0. When you plug in time equals to 2, you get, this is minus 1 and a half plus a half. So before time 2 at 0, the force switches on, y is still 0, but then it starts to change, but immediately right after time 2, like time 2.001, it's still 0, it's continuous, right? I mean, if you think about it, I've been talking about an inverse transform, right? Anytime you talk about inverse function, though, what should you need, Landon? What's the enemy of injectivity? Oh, I'm sorry, invertibility. I just spilled the beans.
Having the determinant be
There's no determinants here, man.
having
No determinants.
if there's some other solution to the zero, the modulus solution.
That's kind of it, right? If you had that,
Something other than x equals 0.
right? If we have more than one thing that maps to 0, that's true. So that's kind of the issue, because if we have, for example, a function which is 0 everywhere, right, except for some discrete set of points, what's the integral?
Doesn't exist.
It's 0. The integral is insensitive to, like, if you have just a finite number of points just sprinkled here and there, what's the area under them? It's 0. It's worse than that. You can even have, count. I mean, you need something called measure theory to really describe this carefully, but the result is that a set of measures 0, well, it integrates to 0, and so those can even be infinite sets. And so it's all of those different, if you take a given function you have a Laplace transform of, you could modify it by doing one of those measure 0 additions, right? So if you think about it, the function and everything else that's related to it, by adding a measure 0 function to it, they give you the same Laplace transform. So then when you take the inverse transform, how do you know which one to pick?
You don't.
Well, we apparently picked the continuous one.
Okay.
So, but in some sense, that's just a choice of the equivalence class of all those other, where the equivalence is up to something that integrates to 0. Yeah. So it's not a true inverse in the sense of strict functional, I mean, like a function inverse.
It doesn't have a unique inverse.
Right. I mean, there's a choice that's made, but it's a standard choice, so it's hard to notice. All right, so beyond that, there's something called the convolution theorem. And it says that the Laplace transform of f convoluted with g is equal to the Laplace transform of f times the Laplace transform of g. This is dark magic. I mean, in other words, the inverse Laplace transform of f times g is just the Laplace transform of the convolution. Wait a minute. Yeah, sorry. So you could see this as a sort of homomorphism kind of result, right? This, in other words, this product in the frequency domain becomes that product in the time domain. It's a sort of homomorphism of sorts. But before you get too excited about it, let me tell you what the convolution is. This, at time t, is the integral from 0 to t of f of t minus v times g of v dv. So there's also some theorems about periodic functions which are worth reading about. You can extend Laplace transforms across series of things too. You can put the series technique and this together. That's also true. In the last 10 minutes, I'm going to use the projector because I want to show you something that I don't want to write out and I can't really derive. So I basically showed you everything you need to solve problems. It's just, you know. One other type of problem I should show you, and then we'll take a little break. And then I'll show you PDEs in an hour, and then that's actually not. I mean, I can do that, not well, but well enough, let's say. Of course, you guys can email me questions as you have them.
Are you here over summer for part of it?
What am let's see, what am I doing over the summer? That's a good question.
I was wondering if you were going to be here for
yeah, I think I'll be around. I mean, I may not be on campus. I try not to be on campus if I can help it. Oh, no, that's not what I'm not sure that I have to look again, but I'm not sure if I ever got to the point of putting my decent, well, quasi-decent notes on the what I'm trying to get at is my handwritten notes are sometimes a little bit better here because my typed Laplace transform notes may not be quite as high quality, actually. Anyway, they probably could use a look through. Come on. All right, here we go. So the direct delta function, is it in frame, Bill? The direct delta function is an interesting thing in that it's not a function. Right? It's kind of messed up. But the reason so here's one glib way of defining it. It's 0 for t not equal to 0. It's infinity when t is equal to 0. You're like, that's not a definition. Like, yeah, okay, fine. I was raised by physicists. What can I tell you? Some things stuck. The integral from minus infinity to infinity, f of t delta t dt is equal to f of 0. That's closer to something that's reasonable. Still kind of weird, right? Because it's saying that that integral, even though it's involving infinitely many values for time, apparently only cares what the value of the function is at 0. But that's a very nice thing, because what it says is that integration becomes evaluation when there's a Dirac delta function involved. It's called Dirac in honor of Pam Dirac, who pioneered the use of these things in physics in the 20th century. He was aware that they were not quite rigorous mathematically. The rigorous mathematics of it's been done for a while, though. I think Schwartz, back in the early 20th century, did it. One use of these would be, for example, for like a point charge. Like, what's the charge density of a point charge? I could use this. The charge density, the density per unit volume of a point charge is Q times delta of R minus A. This puts the charge Q at position A. So this is 0, strictly 0, for any position vector except for A. When you get to A, you get infinity, quote unquote. You get Q there, such that if you integrate a volume integral, if you take a volume integral of rho of R, rho is dq dv, where v is volume. So if you integrate rho dv, you should get the charge enclosed over the volume. And this, if you integrate that charge density, you only get q if you have a volume which includes that one point r equals to a. That's the notion of a point charge. This is the mathematics which you need to carefully describe what a point charge is. Now you could say, well, that's an idealization. Maybe you should think about that in terms of like sequences of functions which converge to this notion in some limit. That actually is how these things were perhaps more carefully discussed, in terms of not a single function, but a whole sequence or sequence of functions which, in some limit they kind of produce this. But so another place you might think about it is like a hammer hitting an object, right? If you have a hammer hitting a nail, you don't really care so much about the details of how it hits the nail. All you really care about is, the net, how much impulse the nail gets, right? How much momentum it has before versus after. And so if you think about impulse, that's the integral of the force over time. So because force is dp dt, so if I integrate dp dt with respect to dt, I just get the integral of dp, which gives me change in p, the net. Oh, you don't know. Sorry. This is August for you. I mean, July, let's say. Anyway, the point is the integral of the force is the change in momentum. So if you were thinking about like a hammer hitting a nail or something, this would be the mathematics of it as well. Some kind of spike that you know the net before and after for the momentum, but you don't really care the details of how the hammer hit the nail. This is also a useful tool for that. You might use a Dirac delta function for that force. That's my point. Where the magnitude, the coefficient of the Dirac delta function would be informed by the net momentum which you gave to the nail. So, of course, in the actual case of the hammer hitting the nail, it's not really a Dirac delta function. It does take some finite amount of time for the hammer to hit the nail, bounce off, right? So the true picture really is more like that. But on the other hand, since you don't know the details, it's a useful mathematical idealization to just say, forget about it. I'm just going to think of it this way, which is basically to give up on these details and just to say I'm considering it the totality of what happened. So sometimes it's that. In physics, I think it's a question of whether you believe point charges exist or not, right? Is there a point charge? If there is a point charge, then there's a Dirac delta function for reals, if you like. No, if you believe in the reality of physics. But otherwise, you can just view it as a mathematical convenience. You can say, well, there really is no such thing as a point charge. Maybe charges are actually smeared out over some finite volume. And this is just a useful mathematical simplification to say, I don't know the details of how that charge is smeared out over that very small volume, so why don't I just call it a Dirac delta function and be done with it? So, which is it? I don't know. Yes, Landon?
So the point of the Dirac delta function is just to kind of tell us what the overall thing is, but not like how it gets to that and then goes back down.
It's a mathematical idealization of an infinite spike with a finite area under it. I don't know if I get what I'm saying, but anyway, the Laplace transform of a Dirac delta function, which you could say, I thought you said we needed exponential order alpha. This definitely doesn't have exponent. Well, I don't know. It's 0 except for 0. Anyway, let's not get into the details. The point is, whether or not you believe it, it's e to the minus as. That's in contrast when I had the unit step function. There's a 1 over s here. So actually, despite the weirdness of this, these are actually easier problems. If you see a problem on your final or your whatever you're taking with a Dirac delta function, you should be happy about it. It means the algebra is easier. Now, if you think about the unit step function, right? What's the derivative of the unit step function? It's 0 everywhere. What about here? We'd say it's undefined in calculus, right? But outside of calculus, which is where we are right now, we would say it's infinity. Because it goes from this to that, it's increasing. In fact, the derivative of this function is the Dirac delta function at t minus a. You can meaningfully write ddt of delta of t ddt of u of t minus a is equal to delta of t minus a. Needless to say, I was quite confused as an undergraduate when I was doing this in one course, and in the other course I was taking real analysis. It was quite a contrast between worlds. I mean, real analysis, I lost points because I didn't say that C was a real number where I needed to use that C was a real number, even though I'd written C was a real number earlier in the proof and I was taught that we read proofs top down. Didn't matter. It's important to say it there. That's why I took off that point. But I said C was a real number like 3 sentences before. Doesn't that count for something? No. And then over here, what's the derivative of the unit step function? And then no one answers. And then he's like, delta function, obviously. And then he laughed at us. Ha 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 ha, you guys, so stupid. Well, I don't know, he didn't say so stupid, but it was there. So like on the one hand, quibbling about whether a real number is a real number, and on the other hand, differentiating things that are not even continuous. What the heck? Anyway, okay. Don't worry, we don't have the physics to get confused on here, so you'll be fine. Anyway, so again, I think that these are, you can view these as just convenient idealizations for something that's smoothed out. Finite time, here's an example. You have a spring mass system, you hit it with a hammer, impulse 1, that would be like this, x prime plus x equals delta t. You take the Laplace transform both sides, you get this, you get that, you get sine t. So basically at time 0, you hit it, and then the thing does sine. If you do a Dirac delta function at later time, you'll see that the solution changes at that later time, like a spike. Let me see if I find one. Yeah, here's one. So here I hit with a hammer, impulse 3 at time pi, and see, Landon, this was the trigonometry I was talking about that was hidden in the details of the example I didn't go through. There's a lot to do there. Depending on how weak you are on the adding angle stuff, there's a lot to learn there. Anyway, you do the homework, you'll be fine. So there it is. Before pi, it's cosine 3t, and then at time pi, you pick up this other term in response to the hammer hitting it. And as you can see, is there a discontinuity? I guess at pi that's 0, so it's still continuous. Let's see here. Anyway, I have more examples in the notes, but ooh. See if there's anything else I missed. We talked about Laplace transforms. We talked about inverse Laplace transforms. Motivated and defined. Just kidding. Motivation up to you. This is from the time before I found the MIT video. I never did figure it out myself, honestly. I mean, I tried. Where in the world is this Laplace transform coming from me? It is a bizarre thing. Anyway, so that's it for now. Let's take a break. We'll meet back again at 11:50. All right? You